first some organizational questions. I'm changing the rules little bit with respect to the previous semester. So you will have some grade for a seminar, okay? So I would like to encourage you to solve some problems in advance.
Do we have a seminar today?
No.
No. Oh.
So today we will have 2 lectures.
Okay.
In a row. So we'll start slow, I think, and I will give you. So next time I will be out of Moscow, so we'll skip next time. I thought to do it online, but I was told better just to skip it because it's recorded. Yeah. So today 2 lectures, and next time lecture, and after that seminar. And so grading scheme for this semester will be the following. Yeah, so I would like it to be, so you will have, so your final grade will consist of 2 parts. The part for seminar and the part for general theory. So let's call it tests. So your final grade F will be minimum out of 10 or 0.6 for seminars plus 0.6 for tests. And for seminars, so to get 10 for seminars, you should be ready to solve 2 problems on a seminar. Okay, it doesn't mean that you will do this, but I will give you like a list where you can say, okay, I am ready to talk about problem number 2 and number 3. Okay, and you're ready means you're ready. You would like to share your thoughts about that, and you thought about that in advance. So 2 per seminar means 10 for S. And tests, it's negotiable. I don't know, if you would like to have some test in the middle, we'll have it. We can do the following. So we can break it into 2 tests, right? And first, for the part which will be in the middle, you'll have 2 attempts basically. So you can, take a test in the middle. If you don't like the result, you can take this part at the end as well. If you wish, you can do this. Okay, then what we'll discuss in this semester.
So there is no examination, it's only seminars and tests?
Well, final exam is the test, kind of. Yeah.
But how it will be estimated? That's fine.
So that's how.
Yeah. So, but we will not have any tickets with problems.
Yeah, I think on a final exam you will have like these tickets. So the general theory is kind of it's harsher this time, and to just for you to answer just one particular question over the whole semester, it's kind of it's hard to remember, and of course it's open notes, but yeah. So I would like the seminars to play more in this game. So that's why. All right. So what we will discuss this semester. So first big part is structure theory of Lie algebras, well, finite dimensional Lie algebras, we will start with nilpotent and solvable, and then the most important and the beautiful part of this theory is structure theory of semi-simple Lie algebras. And this will actually lead us smoothly to representation theory of semi-simple complex Lie algebras. So, theory of well, let's say simple rather Lie algebras. Also finite dimensional, so last semester we talked about SLN and SL2 a lot. So this time we'll see how all this generalizes to any complex simple Lie algebra. Yes, and so in these two parts I will follow mainly Kirillov Jr. book. So Kirillov book. Kirillov, Introduction to Lie Groups and Lie Algebras. So, Kirillov, Introduction to Lie Groups and Lie Algebras. We actually, so this semester, so for this semester, for these two things, we start with chapter 5 there. And, well, skipping some parts there, maybe adding something that is not there, we'll go to the end of the book. And chapter 5 is in the official print by Cambridge University Press. Also, there's this version on Kirillov's website, and numbering there is a little bit different. So I am talking about Cambridge University Press version. And then we'll see at which point of semester we are, but then we kind of go to higher levels. We can talk about infinite dimensional Lie algebras. Well, there are a lot of them, but ones that follow, they kind of admit a version of the theory that we'll discuss in the first part of the semester are called Katz-Moody Lie algebras. And in particular, as a part of this, so in particular, affine Lie algebras. So these are infinite dimensional Lie algebras, as I said, which actually admit similar theory to what we'll discuss here, but even more, like some imaginary roots, so affine Lie algebras, they are like central extensions of some algebra, of loop algebras, so-called. And these are your favorites, I think, right? Because you heard of them on other lectures, right? So so this appeared as some symmetries in conformal field theories, if you wish. And then another thing that I would like to talk about, but we'll see, maybe we'll have time for that, maybe not, is can be called Fourier analysis on compact Lie groups. Yeah, it's another beautiful part of Lie algebras, of the theory of Lie groups and Lie algebras. Right. So, for example, Weil's formula can be obtained in a different way, can be proved. And historically, it was proved using compact Lie groups, rather than algebraic proof that we touched last semester. Okay, so the book for this one will be the Victor Katz itself book, which is called like Infinite Dimensional Lie Algebras, if I remember correctly. And for this one, I'm still indecisive. So, but my choice number one would be maybe Zhelobenko, which is called like compact Lie groups. It's a big book, and actually all that also can be found there. There's a bunch of books which has all this theory, but I think what was in Kirillov's book is kind of more or less essential for a mathematician or physicist, which is, I don't know if there's too much difference nowadays. Well, there is. Anyways, so for this, let me mention Zhelobenko. Compact Lie algebras. Okay, so that's it. And yeah, of course, yeah, I already had some requests, what we would like to discuss. So some of these requests, I think, will be satisfied in the part 3. All right, so let us start. And first theme first theme is called Solvable and Nilpotent Lie algebras. Let us agree for until stated otherwise that when I say Lie algebra, it's finite dimensional Lie algebra. So until the middle of semester, I guess. And it's by default it's over complex numbers. Okay. it's not. It's always a good exercise to think if what I say works over real numbers, or if you can deduce it maybe by different means for real numbers. Okay, but majority of theorems that I will be talking about is also true for reals, and moreover, application to compactly algebras. Yes, it should be compactly groups here, right? Yeah. Yes, and of course, application to compactly groups is makes sense more or less when we talk about real Lie algebras. Anyways, so that's our agreement, finite dimensional over C. And you might think and ask questions whether it's true or not for R. All right. So let's just start. Let's just recall first what is a Lie algebra. So recall a Lie algebra G is for us finite dimensional vector space. And with a linear map. So it goes from, it's usually denoted by these brackets, right? And it goes from G tensor G to G, such that, okay, it should be first antisymmetric, right?
It should be bilinear map, right?
Yeah. So from tensor, so when I say it's linear from tensor to here, it means bilinear, right? Or you're right, I should add the by here, and maybe instead of O times, right times, right? Yes. And here we should have this. And what is the second condition for this bracket? Jacobi density. Right. So you should write it like this, right? So cyclic permutations of brackets like this. Equals 0, and inside I should write x, y, z, and then z, x, y, and then y, z, x. All right, so next notion that we're going to recall, we never talked, I think we talked a little bit about this notion last semester, but we didn't need it too much. Notion of an ideal. So a subalgebra, Lie subalgebra, should try it, right? A Lie subalgebra I inside G is called an ideal if, so, well, this is a definition of an ideal, so let me indicate that. For every h, so for every h in I and g in, well, element x and g, if I take a bracket h with x, it still lives in I. Right? So it's subalgebra means that it's closed under, it's a vector subspace, first of all. It's closed under taking brackets. But it's more than that. If I take something outside of this subalgebra and take bracket with something which is inside, it's still, you still fall into this thing. All right? So this is the definition. And for example, so note that there's no difference between left and right ideals here, right? So for maybe you thought of maybe you heard of ideals in rings, where there's difference between right ideal and left ideal. Here there's no, because of anti-symmetry of the bracket. Okay, so examples include intersection. You can check it yourself. Also, the sum. Also, also you can check it yourself. So the sum is just as a sum of two vector subspaces, right? It's a bunch of elements such they are represented as a sum of elements from here and from here. And another thing which will be important for us is I1 is what's called commutant of two ideals. So this one, let us discuss a little bit more in more detail. So this one is what is exactly what you think. These are span of elements of the form x bracket of x1 and x2, such that x1 belongs to I1, x2 belongs to I2. So let's see that this thing is actually an ideal. So we should check that if I take x, right, from I1, I2, and if I take y from whatever, from G, right? So both I1 and I2, they are ideals in G, right? Then the bracket should be inside I1, I2. So that's what we would like to check. In particular, this would mean that this subalgebra, right? Because I can take y inside here as well, then bracket will be closed. It's arithmetically a vector subspace. So let's check this. So x is then well, let's assume first that it is pure commutator, so like that. Then we have x1, so assume x1, x2, bracket with y, And then we should use the Jacobi identity. All right. So, yeah, you should help me out, right, here. It's very, very hard to transfer brackets. So what I know is that a bracket, yes, okay. Let's just apply this, right? So this is the same as I just cannot as this, right? And this is then the same as x1 and then x2 y x1, right, plus x1 and then x2y. Right. So this thing is from, so before the problem was that this thing is not in our ideal, right? Not in any ideals actually. So but this one is in I2, this one is in I1. We know that I2 and I1 are ideals, therefore bracket with something in ideal is also an ideal. Right, so therefore this one is in I1, this one is in I2, but moreover, yeah, then they are in a span. Yes, but we need in here. Right, but so this one, I should rather say that, okay, this one is in I1, right? Therefore, this one is in I1, this one is in commutator. So this one is in I2, therefore this one is in I2, this one is in commutator. So then span, and therefore, by definition, it's in here. So I put maybe so yeah, so this one is in I2 and this one is in I1. That's what I should have here. This is in I1 and this one is in I2. Anyways, we're done. Okay, so commutant of two ideals is an ideal. This will be important for us. So consider Lie algebra G, and let us define what's called, so definition of what's called derived series.
Excuse me.
Yes?
Can we make a statement like I1, I2 commutator itself belongs to, say, I1 or I2?
It actually belongs to an intersection.
Okay.
It's smaller than intersection.
Okay.
Yes. Yeah, thank you. Very good. So suppose I have Lie algebra. So consider Lie algebra G. Then derived series is an infinite series of ideals inside G. So then derived series is a series of ideals, and we'll denote them as D with upper index I, G, and di plus 1 will be inside di. You will see why. Defined recursively I don't know how to spell it. Anyways, as follows. So D1 is just a commutant. And then DI with I greater than 1 is di minus 1 g di minus 1 g. All these things are ideals, and moreover, di plus 1 g is inside di g, right? Because the commutant of di g. Yeah. So a commutant can be of two ideals, right? But when I have one ideal and I say commutant, I mean just a commutant of this ideal with itself. Okay. Okay, here comes another definition. Lie algebra G is called solvable if D n G equals 0 for some n. So its derived series stabilizes at 0. Proposition let us find an equivalent condition for G to be solvable. G is solvable if and only if there is a sequence of subalgebras like that. So we have A0, which coincides with G, and then A1, A2, and so on. And well, the last one well, not maybe some AK, right? And AK is actually 0, right? So 0 belongs to the sequence of ideals, such that well, first of all, A I plus 1 is, so this is a sequence of subalgebras, as I said. But AI plus 1 is an ideal in AI. And AI plus 1 mod AI is an abelian Lie algebra. Is abelian. So this is a big condition, almost as big as definition of derived series. But so this are usually that's a convenient thing how you prove that algebra is nilpotent, solvable. We'll have nilpotent Lie algebras, and we'll have similar stuff for them. But for now, it's solvable. Okay. So let's prove that. Proof. So this way, very easy. What should I do? Yeah, so I take AI to be DI, right? And that's it, because so they're all ideals, one inside another, so therefore one inside another is also ideal. I need to make sure that AI plus 1 quotient by I is abelian, right? But it's just AI plus 1 quotient by, this is just AI plus 1, AI plus 1, right? Maybe we should be accurate with indexes. So let us. So let me see. So D0 is G, which is I minus 1. Yes, very good. So here's some mistake. I minus here, and here as well. Yes, right, because I minus 1 is bigger. Yes, very good. So, right. What I would like to say, it's like this. Right, because AI is DI like this, right? DI G, which is by definition DI minus G, DI minus G, DI minus 1G. All right, and this is again by what we said there, AI minus 1, AI minus 1. Right. Is it clear why this is abelian? Prasun, do you understand? Okay. We could just kill all the commutators, right? Should be abelian. All right. So all conditions are satisfied. The other direction. So suppose I have this, then I would like to see that my derived series stabilize at 0. For that, I would like to, so let's prove that AI contains DIG by induction on I. Then we will be done, right? Because because then dkg will be 0 eventually, right? If my ak is 0, so all right. First, how about I equals 1? Right. A1, well, A1 maybe A0, right? Even better. A0 is just G, right? And D0 is G, right? So it contains D0, which is G itself. All right. Right. So then let us do the step of induction. So I have right. Maybe I should start with dig, right? It is di minus 1 g di minus 1 g. So this one is inside I minus 1. And, well, and this one as well. Right, so this is inside commutant ai minus 1, ai minus 1. Right, but I claim that this is actually inside ai because I never used that ai over ai minus. So, right, I never used that ai minus 1 over ai is abelian, right? So therefore, actually, the commutant of this thing is the largest subalgebra that such that if I quotient by this, I will get abelian algebra, right? Therefore, it but if I get it means that the largest means if I have something, if I quotient by this something, I get abelian, then no, the largest, the smallest, right? Then the commutant is inside, right? So this is because and that finishes the proof. Of course, not the largest, but the smallest. What is the largest algebra inside G such that if I quotient by G, it's abelian? It's G itself. Yes. The smallest is the commutant. All right. So now let's talk about nilpotent Lie algebras. So definition, first let's define some other series which is called lower central series. Again, let us have a Lie algebra, and we now define D with a lower index. Okay, D1 is the same as with upper. And then D, after the second, after the first one, they start to differ because DIG is G with DI minus 1G. So this one is larger. And definition, Lie algebra G is called nilpotent if D and G equals to 0 for some n. Okay. So you maybe heard of the word nilpotent in context of rings or maybe matrices. So what is a nilpotent matrix? Some power of an element, right? So here I'm actually thinking of a power of a matrix which is representation of an element in unjoint representation. So this is kind of connection here, but we'll make it more precise later. And this is what's called Engel's theorem, that and a Lie algebra is nilpotent if and only if add x is nilpotent for every x. Add x is an image of an element x under unjoint representation. All right. Very nice. Okay, so the proposition, the same as in the previous case, proposition. G is nilpotent if and only if there is a sequence of ideals in this time such that, which sequence? So again, G is A0, then A1, and so on. Everything ends with 0. Such that if I take commutant of G with AI, it will live inside the AI because AI is an ideal in G, right? But we want more. We would like this to live in one step smaller A, which is I plus 1. That's it. So let's prove that. Again, so proof. This way is very easy. You take AI to be DIG. And this, well, okay, so is it obvious or we should check something? So let's see. You should, well, it's just this one is just a definition of the lower central series, right? It's just recursive definition like this. So nothing really to check. These are ideals. They are included in one side, other. So this is done. So the other way, again, the same idea. So let's prove that AI includes DIG by induction on I. Again, for A0, we are done. Well, for I equals 0, right? And then for the step of the induction, let's see. Right. So again, let us try to use the just definition of DI. So DIG, we would like to see that's inside AI. So this is by definition G with DI minus 1G, right? So this guy, by the induction assumption, is inside AI minus 1. And here is even more easier, right? And G with AI minus 1 is inside here, right? Here index I is one step higher, so we should write here AI, right? And we are done. Okay, very nice. So what usually do you think about when you think about solvable and nilpotent Lie algebras? So the most natural examples are upper triangle matrices and strictly upper triangle matrices. And let us actually formulate it accurately now. Consider a full flag. Full flag, what it is? It's a bunch of subspaces in a vector space, right? So it's a collection of subspaces V1 inside V2, inside V3, and so on, and Vn. Such that dimension of Vi equals to I. So that's this what it means for a flag to be full. Right? Each time dimension increases by 1. So Vn will also, so all these are subspaces of Vn, right? So Vn, let's also denote it as V. All right. Now we would like to consider some subalgebras inside all linear transformations of V. So first one, which will be upper triangular matrices. These are all x from GLV such that x of Vi is inside Vi. Never goes outside of Vi. And then N of F, these are all linear transformations of the space V such that if I apply it to some element x from N of F to Vi, it will jump to V with one index down. Right, so if you, what's going on here? If you fix a basis in V such that V1 is spanned by X, by V, so suppose your basis is like this. So V1 is spent, is just spent on vector W1. It's one-dimensional space. Then V2 is spent on W1 and W2. And then V3 on W1, W2, W3. Then in this basis, these are upper triangular matrices. These are strictly upper triangular matrices. Right? So what we would like to say about this, just that, so proposition, let me maybe write it here. So B of F is solvable. And N of F is nilpotent. Let's prove it. We will prove it using our criterion of solvability and nilpotency that we just obtained. Let me see. What should be this subalgebras AI? It's kind of clear. I should choose AI, so proof. Denote AI to be the following things. X in GLV such that if I act, maybe not, maybe AK, too much I's. So if I act on VI, then it sits inside VI minus K. right? So these are subalgebras of B of f and N of f. And moreover, they are ideals in there. So let us see. So first of all, this I claim that A case, A1, and so on. How much do we have them? AN maybe, right? So AN is already 0, right? Or not, right? So, so I have A0. So first, let us notice the following. So A0 is who? It's B of f, right? A1 is N of f. So which A becomes 0 first? I think it's AN, right? AN, just because we don't have V0, right? And Vn is the whole thing, right? Yes. So N is just 0. And all this A1, A2, and so on, up to AN minus 1, are subalgebras, first of all. Well, in GLV and or in B of f, if you wish. So let's compute commutant of AI and AJ. I would like to, what I claim is that it's inside AI plus J. So we kind of assume that AI, where I greater than N is or equal than N, they're all zeros, right? Just to make things clean here. So that's what this formula means. Indeed, why this is true. So the commutant consists of linear combinations of commutators, right? So I have x, y minus yx, for example, is in here, where x is in AI and y is in AJ. So it means that if I take something in VI, I first act by a composition shifts this index by A plus J. Do you agree? And doesn't mean which way. Of course, the result will be different, but still the index will be shifted by I plus J. Right? So we first shift by I and then plus J. By J. Here first by J and then by I. So this one sits inside AI plus J. And therefore all linear combinations as well. In particular, this means that they are ideals inside B of f, right? Because if I take something from B of f and like if I take AI and something from B of f, right? then it will be in A with I with index greater, which sits inside AI. Right? Therefore, AIs are ideals. So in particular, AI, or A1 and n-1 are ideals in B of F. They are not ideals in GLV, by the way. But in B of F, they are. Very good. But this also means the following. Nilpotency of N of F immediately follows. Right? I claim that A, so this time A0 is B of F. Yeah, everything is fine with, matches our previous notations, right? So I claim that AI minus 1 mod AI is abelian. Why? Because AI minus 1, so if I is greater than 0, then this happens. Because we just proved that AI minus 1 is inside A to I minus 1. 2I minus 2. Right? Which is inside AI for I greater than 1. Agree? So therefore, commutant of this sits inside a quotient by commutant by something, and so in particular a quotient by commutant as well. So I get an abelian algebra. So this is abelian. Therefore, so abelian because this. Therefore, N of F is nilpotent. Right? Why? Because I have N of F. It's the same as A1. And then I have this sequence of ideals. A1, A2, A3, and AN is 0. Such that this is abelian. Therefore, according to our criterion, this is nilpotent.
Solvable corresponds to nilpotent.
Yes. You're right. So something is messed up, so let's try to fix it. Yes, so solvable means that maybe not this one. So let us, so maybe we rushed it a little bit. Yeah, so for solvability, for nilpotency, I need what? So again, N of F is A1, and then I have A2, and so on, and this is 0. So for solvability, I need A1, right, this one we also have, with AI. Sits inside AI plus 1, right? Say it again.
Oh, yeah, 0 is 1. Okay, no problem. Sorry.
Yes, for n of f, yes. For b of f, we will need a0. Right. So, but this one is just that's exactly what's written here, right? So therefore, n of f is abelian, sorry, nilpotent. Okay, what should we do with b of f? So with b of f, we have almost everything except a0, right? So for b of f again, so b of f is a0, and then inside a0 we have a1, a2, and so on. And we should check that I minus 1 over ai. Yeah, so here maybe I should write 1 because I started with ai minus 1 here, right? So this is abelian for all I starting from 1 greater or equal to 1. So that's what we would like to see. What we saw that for all I greater than 1. Right? So now we should check that a0 by a1 is abelian. And then we will be done. So, right. So we have to consider a0, a0. Commutant of this thing. So suppose, well, by linearity we can suppose that just take a commutator in here, right? So what lives inside here are linear combination of commutators, right? So just take a commutator. So both x and y belong to a0. So I would like to see that this is inside a1. That's my goal. Very good. Here I should go to manual mode, if you wish. Right? I really would like to use. So what was before that didn't require the flag to be full. Like if you trace all the proof, it works fine for partial flags too. So here I really need a full flag. Why? Because, well, I take this commutator, right? So I apply x So I take a vector v from vi, right? And suppose that, again, suppose that w1, w2, and so on, wn is a basis, as we discussed, of v, such that vi is a span of w1, wi. Then v, vector v small, is just ci wi plus something else that belongs to v with index less than I, right? So ci maybe minus 1 wi minus 1, and so on, c1 w1. So now let me take x and y and apply it in one order and the other order to v. Let's see what happens. So if I have wi, right, and apply x to it, I will get something which is, say, ai wi plus something which is index is smaller than I. All right. And if I take y and apply to wi, I'll get, say, bi wi plus index is smaller, right? Now, this means that if I take x, y, apply it to any vector v from there, right? I will have ci and then ai bi wi plus from other spaces, as things from other spaces. And the other way, the same coefficient here, right? I just first I get bi and then ai, right? But the multiple will be the same, right? So when I now take difference of these two things, right? So therefore, xy minus yx applied to v, this already lives inside these dots, right? Because these two coefficients. But these dots, they live in vi minus 1, right? So we are done. So therefore, commutator lives inside A1. And therefore, A0 by A1 is a billion, because commutant of A0 and A0 lives in A1. So 4 minutes for a very easy observation, maybe a couple of them. You might ask me, what's the relation between nilpotency and solvability? Maybe one implies another, on the other way around. Or maybe they're equivalent, I don't know. So what do you think? nilpotent implies solvable, right? Well, you can think of upper and strict upper triangle matrices, right? If you have, it's a good example. So it's not like everything behaves like in this good example, but like you can think of this good example and ask yourself a questions, right? That's true. So one simple thing, but still it's, well, we'll apply it a lot, is that nilpotency is stronger than solvability. So proposition, I don't know. Nilpotent Lie algebras are solvable. I don't know. Let's prove this. We'll just note that D with upper index is inside D with lower index. Why is that? Let's see, maybe we will need induction, but let's see. So D with maybe even no induction. So let's see, DI G, it is this, DI minus 1G, DI minus 1G. Right, this is inside G, right? Therefore, this is inside D with a lower index, right, by definition. So that's it. Another very almost obvious thing. So note, maybe not even as a proposition. An ideal of solvable G is solvable just because derived series of an ideal lives inside derived series of an algebra. Okay, and actually, even weaker statement is subalgebra. If I change here ideal to subalgebra, so a subalgebra of solvable G is solvable. Still true. Is it right? Yeah. So let's check it. So if I have a subalgebra, then I claim that D. So subalgebra. Suppose H is subalgebra inside G. And then I claim that DIH is inside DIG. Yeah, so this is true. Yeah, this should be true. Right? Everybody agrees. Just because DIH, it's recursively it's a commutators, but both parts of this commutator is inside H. So I don't need the property of an ideal because both parts are inside this thing, right? So it's closed under this. What about quotient? Quotient is as well.
Yes.
Quotient by ideal is as well solvable. Let us put it on board. So quotient of a solvable Lie algebra by an ideal is also solvable. I leave it for you to check. And what about nilpotency? So for nilpotency, I really need an ideal here. Because in the commutator, I take the whole algebra and then Dij, right? So an ideal of a nilpotent Lie algebra is nilpotent. And quotient of nilpotent Lie algebras is nilpotent. Because taking quotient is actually Lie algebra homomorphism to respect brackets. So that's why. Quotient of nilpotent Lie algebras by an ideal is nilpotent. You might also ask, so suppose I have some algebra. Now I want to cook up like solvable Lie algebra out of solvable pieces. Direct sum is not so interesting. So suppose I have a solvable ideal and quotient is solvable. Is Lie algebra solvable? The answer is yes. And so that will be the first statement of after the break. Okay. So you might have a Lie algebra with an ideal which is solvable. You don't know anything about Lie algebra itself, but ideal is solvable. And the quotient by this ideal is solvable. Can you deduce that Lie algebra itself is solvable or not? So you can, actually. And it's also an easy statement. So let us fix it after the break. But only for solvable. For nilpotent, this is not true.